Okay, thank you very much, Pierre. Thank you. So, as Pierre said, my name is Mathaios Panteli. I'm currently an assistant professor at the University of Cyprus. So, I see a few new faces in the audience, so I will quickly introduce myself before we go into the presentation. So, I did my undergraduate degree in Greece, in the Aristotle University of Thessaloniki in the north, in northern Greece. Then my PhD in the University of Manchester, where I stayed for some years as a postdoctoral associate. Then I was a lecturer in power systems, and I was also the deputy head of the energy systems cluster at the division of power energy systems. And then the last 3 years I am with the University of Cyprus as an assistant professor, and also a faculty member of the GEOS Center of Excellence. So so as Pierre said, we already delivered 3 lectures as part of this position. So we started from March, where we talked about resilient power systems, then how we measure, how we enhance power grid resilience, cascading and dynamic studies, and then this last lecture will focus basically on flexibility of sustainable systems. And we'll see a bit of examples about multi-sector and multi-vector next perspectives, and how everything is brought together into under joint frameworks to try to co-optimize different energy vectors and different sectors together. So as we all know, I mean, the power system is evolving itself. So starting from the vertical structure that we had, starting from the generation and moving to the consumption, now everything is getting more complex with the penetration of electric vehicles, of renewable energy sources all over the place. So we see this kind of multi-directional and bi-directional flow of energy systems nowadays, and looking ahead in the future as well. Also, the multi-sector and multi-vector perspective is becoming very important. We have now different energy carriers that can provide different services in the grid. As we can see in the left-hand side here, we have different new technologies coming in, heat, hydrogen, gas, and so on. So everything is becoming more and more interconnected and also interdependent, which also leads to higher interdependencies between the critical sectors, or now critical entities, as the European Commission calls them, in the new directive they have for resilience of critical entities. So we can see this diagram here that basically electric power, the power system is at the heart of the backbone, let's say, of the critical infrastructure upon other critical sectoral dependence, such as natural gas, water, transportation, and so on. And within this lecture, we'll try to cover basically some of these interdependencies, and I will go into much detail about the Future and Dams project we completed from the time I was in Manchester, which was looking into water, energy, food, and environment sectors. So when we talk about multi-energy system integration, we basically have, as we can see, this sunken diagram, which I find quite representative. We have the energy carriers on the left, coal, gas, hydro, wind, solar, and so on, which are providing all these kind of services, heating, cooling, electricity, lighting, and so on. And the important thing is how we kind of co-optimize these kind of different energy carriers within this multi-energy environment that we have as an evolving system now. So we have different technologies coming in the system. We have gas boilers, we have electric heat pumps, and so on. And the question, as I said, is how we bring everything together and we try to co-optimize, in a way, these kind of technologies in these resources in order to provide the services that we need as a society, for example, heating, cooling, electricity supply, and so on. So traditionally, what we were doing, we're having the power network, for example, we're having the gas network, and then those two systems were providing the electricity and then gas demand in an independent manner. Now, if we're going to be talking about the coupled approaches, we need to be looking into the interdependencies and the integration of the two systems together, as we can see in this simple diagram here. And also, if we start adding more critical sectors, for example, transportation, heating as well, as we are considering future energy scenarios, then the whole complexity and the whole integration is becoming more and more critical for future energy scenarios. For example, National Grid in UK, they have this kind of, as they call them, the future energy scenarios, where they have different energy carriers and different low carbon technologies penetrating the system, which will be operated, and they have to be co-optimized in a holistic manner. Further to the multi-energy perspective, we also have the multi-sector, and this is just basically an example of a multi-layer analysis where we need to define the coupling points between the critical sectors in order to assess basically their performance, their vulnerabilities in a coherent manner in order to co-optimize their performance in a multi-sector environment. And this is just an example of a water power system integration, which I will be talking more about in the future, where basically we can have at a high level or high voltage level, we can have as a coupling point the hydropower between the water and the power system. And looking into the water and power distribution systems, we can have water storage tanks, water pumps, and so on as flexible demands looked from the electricity perspective. When we started the project, the Future NAS project, which I will talk about later, we're doing our thing here as electrical power engineers, and the water engineers were doing their part from the water side. So basically, as power system engineers, we assume that we'll have plenty of water to use whenever we want for hydropower generation. And the water engineers from their side, they were putting their own constraints on the water that the electricity part will have for hydropower generation. So when we're actually trying to merge the two, we actually realized that it's not that simple. And as I will say later, there were many complexities in coupling the tools, both from the perspective of modeling each system. They run in different time resolution. For example, we assume that once we open the valve of, in the reservoir, the water would go automatically in the generator and start producing electricity. The water engineers told us that's not the case. It takes some time. So that time resolution, that time difference is very important to consider if you want to achieve high accuracy in your results. So, okay, this is something that we said already. So the first case study that I will talk about is the Manchester campus case study. So this is a representation of the new campus of the University of Manchester. So we're actually tasked by the dean of the university to see how we can co-optimize the energy resources we have in the campus. So in the campus, there was the electricity, the heat, and then gas systems, which were kind of operating independently. So we had our electricity, our heat, our gas demand, and were supplied in a kind of independent manner. So we're tasked basically to see how we can run this within a multi-energy environment and how we can basically achieve some savings in terms of some key indicators they gave us, which is basically the CO2 emissions, the cost reduction in energy consumption, and so on, as I will explain later. So in a nutshell, the district of the university is comprised of 26 buildings that are owned by the university. Some of those buildings are connected to the same electricity distribution network, district heating network and gas network. So some of them were already on the same network, but most of those were not. So these are just some characteristics about the district on demand of electricity and heat as well. And we're given basically a baseline of the energy cost and carbon emissions to use as a benchmark within our analysis. So what we did first the decoupled energy services. So we looked how the system behaves if we look at the electricity system and then gas network independently in order to provide basically the services we had in the campus in terms of electricity and heat consumption. And then we simulated within our models the boilers that we had, both at the local and at the district level, to see their efficiency. And then we put into that as well the heat network, the heat losses, and so on under a common framework. Then we started mixing a bit the things. So we also started considering the ambient heat and how we can utilize that in order to operate basically our heat pumps and both again at a local and district level. And then what we did afterwards, we actually put in the system, in the simulation, the gas network as well as a common framework. So we then noticed that basically we can reduce a lot the grid electricity consumption. We can utilize more than gas supplies that we had, which is a cheaper option, at least in UK, because gas is one of their primary electricity supply. And then basically we saw with these stacking diagrams how moving from the decoupled energy services, how we can basically move into a multi-energy perspective to see how we can co-optimize and co-utilize the heat and gas and the electricity vectors. So what we did afterwards, we kind of defined different scenarios, different cases, starting from the baseline, then moving into a conservative scenario, where we, as you can see here, with the boilers, we kept them steady. And then we tried to increase the PV, the electricity heat pumps, and the combined heat pumps that we had in the system under 4 different scenarios. We had the baseline, we have a conservative, a modest, and an extreme, basically, penetration of these low-carbon technologies. And these scenarios were basically developed with the technical services from the university to see what is actually possible to do with the infrastructure we had in Manchester. So you see that we put a lot of PV as well, which was a bit funny to do in Manchester, considering the cloudy weather, but it actually worked. So in this table here, we can see basically different indicators. So we have the annual economic savings, the annual carbon savings, the peak in demand reduction, and the electricity demand reduction. So this is the business as usual. So basically continue operating the system as it was, but within these technologies for the different scenario. But also what we did, we applied some smart control. So the problem that we had with the technical services was, at the beginning they told us you can only monitor what's happening without having any action on the boilers, on the heat pumps and so on of the campus to control their operation. But later on during the project they gave us some access as well to the actual assets that were in the campus to start controlling those and start seeing the benefits on the system. So we can see basically this is the reduction that we achieved from each of the scenarios. So you can see that there is a big reduction. Of course, if we move to the extreme scenario, of course, we have the biggest reduction in all the indices. But the important thing is, and the interesting thing, is that they actually adopted this kind of modest approach. So they installed more PV, they installed more heat pumps in the campus. And over the years, we completed this study about 4 years ago. The savings are actually quite close to what we calculated through our model. So basically, this work helped a lot the University of Manchester to actually achieve a lot of savings, both in carbon emissions as well as electricity and heat consumption. So taking a closer look basically at this diagram, so here we have the CO2 emissions and we have the cost in the x-axis. And here we see basically that even though with the extreme scenario, the cost of investments is higher, okay, the annual savings on the electricity and the heat consumption actually come to kind of counterbalance the initial investment that you put in your assets. So although the extreme scenario was requesting, and it was requesting more investments, we see that basically if we consider the net present cost, it's actually not that expensive, of course, over a long period of time to actually get back all the, to actually return the investment that you put forward for the assets. And this is just a value flow map that we created as well for demand side flexibility, because what we're asked also is to basically try to see if the services that were provided and that were added in the campus can actually be used to provide flexibility services to the grid. So this shows the value flow map for demand side flexibility, where basically the demand side flexibility of the campus was in the middle there, as we can see. And then we have on top of everything the TSO, the DNO, the retailers, which can act as, let's say, aggregators. And then we have here the flow of energy, cache information, in order to provide more information to the University of Manchester. You can interrupt me for questions if you have, or we can discuss everything at the end. Okay? So this is an example of a sort of multi-energy integration. So talking about a bit about resilience, so Pierre will not have a complaint that we left resilience out. A piece of work that we did with some colleagues recently, we basically took this resilience trapezoid that we had in a previous publication of ours from 2017, where basically it has these three phases, where we have a disturbance here, and then we have the progress of the disturbance, which reduces the performance of the network, whatever the network is. We have this period where you are trying to basically coordinate your emergency actions, and then we have the restoration of the system back to its initial state, or there are some discussions that after a disturbance you can go into a better and more secure state with the appropriate actions. So the question that we asked with some colleagues in a publication we had last year is how a disturbance from one energy vector can escalate or propagate to another. So we basically created this kind of conceptual frameworks where we had the resilience trapezoid for electricity network, heating network, as well as gas network. And then we kind of came up with a conceptual kind of framework to see how, as I mentioned, a failure can propagate from one energy sector to another. So at specific points of this kind of network performance, what happens if there's a disturbance, for example, in the gas network, and how can that propagate to the electricity or to the heating network? Unfortunately, this is a work that didn't proceed yet. So this is something that it's in my agenda, let's say, to look into more detail, because it's for me, it's a very interesting topic to examine. So if you have any ideas or any spare time, I will be very happy to discuss this to see how we can quantify, let's say, this kind of different curves for different networks and to put them together, let's say, under one single framework. Okay, so I'm open to ideas and suggestions.
Mathaios?
Yep.
Can you also say something about the data requirements, like how easy or difficult it would be to sort of find the correct parameters and being able to do such an analysis?
Yeah, for the electricity part, we have it.
Yeah.
that we have, yes. I mean, the first thing you need to do is to actually simulate, I mean, to have a multi-energy system. That, again, we can do. Then, the difficult thing is how you can actually simulate a disturbance in one system that can propagate to another. That is where, unfortunately, the researcher that was working on this paper, she moved positions afterwards, so we were not able to carry on working with her. So the difficulty that we're having is that you simulate a disturbance in one network, how that can affect the other, because as you know as well, the time and the spatial resolution is very much different. With regards to data, I mean, it depends how complex you want to do it. If you want to do it quite accurately, then you will need quite a lot of data from all the systems to...
Yeah, because what I was sort of thinking, right, I don't know if you have some electrical equipment, you have a low voltage right-through characteristic, so let's say it will not disconnect, but then does the equivalent of that exist, let's say, on the gas counterpart, low pressure right-through for a
yeah.
or something like that, and might not be very straightforward to get all these things together.
It's very challenging, and also I'm sure you know Pierluigi Maccara, yeah. I mean, you were there as well. Yeah, I forgot. I mean, he did a lot of work on electricity and gas networks. And it's something that we discussed with him as well to do it. But once we started doing it, I mean, the complexity exploded. And he told me, okay, mate, let's leave it for now. I mean, the Texas example is a great one. What I told the researcher to do is to try to get as much data from that blackout and try to translate that blackout into modeling. But unfortunately, she left.
Yeah, I know in Italy it's a good approach, sort of reverse engineering.
Yeah. But I mean, as I was saying, I mean, if, for example, if as the performance of the electricity network reduces here, and you have, for example, a disturbance in the gas network at some point, how would that affect this? If it drops faster or if it doesn't or whatever it happens, that would be something amazing to do, at least from my perspective. So we can discuss it further later if you want.
We have some people here who have gas power plants, so.
Yeah.
But this trapezoid, if you talk to the storage system there, they were trying to regulate the ENSO and this kind of stuff, also the storage thing.
Yes.
Inside the distribution network. So this trapezoid is, in the future, is going to be a reality or to change?
The trapezoid, I'm very much aware and self-aware that it's not really a trapezoid. When we first working on this, what I wanted to achieve is to have a simple way of showing what might happen for a disturbance, when you have a disturbance. When you look into real data, first of all, this period is not that long, so it doesn't take that much time, but I wanted to have a nice shape to be kind of explanatory. What we do in different projects, you are very correct. When you want to do dynamic studies, for example, when you look into dynamic stability, so you have the drop, and then you immediately go back to service, as you said, with batteries, with quick injection of energy, let's say, you can recover much faster. Yeah. We do that, and that was a topic of the previous lecture, but I can share the slides. Yeah. Thank you. Okay. So, I mean, on this topic, when we're talking about resilience of interdependent systems, we have all the suppliers, different, as we're saying with Hakan now, I mean, we have different metrics as well that different networks are using. So when you are adding resilience as well in the picture, we need to define power and gas metrics, water metrics, transportation, telecommunication metrics, and the question there is how you can actually try to compare or to come up with a common metric system that will be acceptable from the respective operators and regulatory authorities. In UK, that I'm still working a lot with, we have discussions with Ofgem and with Ofwat, which is basically the electricity and gas and water regulators. And we had also INGEM, the Institute of Gas, I don't remember the, INGEM and National Grid as well, where we're trying to build the electricity and gas equivalent network of UK and try to expose that network to different kind of disturbances, which was basically inspired, if you like, from the unfortunate example of Texas. And they were worried that if a big gas disturbance happened in UK, what would happen in the electricity sector? And also with the water system, of what were very interesting to see how the water consumption of big thermal power plants will change under the impact of climate change, and looking into climate resilience, how much water the electricity sector will need, and how much the water licenses that the electricity authority will have to pay will change as a function, let's say, and dependent on the water scarcity that is expected as an impact of climate change. So looking into this kind of interdependent side of critical infrastructures, in Manchester we started this FutureNet project in 2018, which was looking into the design assessment of water, energy, food, environment megasystems. So there is a video. There is sound as well. Good. So I will leave the video explain what the project is. Okay. So this project is probably the one that I'm most proud of. And it conflicts completely the usual academic, let's say, metrics, which is publications, these kind of things. Within this project, we had 3 case studies. So we had a case study in Ghana, looking at the Volta River Basin, and try to build basically these kind of optimization models to make better use of the water resources that they had in the river basin of Volta. We had a case study in Nile, in the Nile Basin, connecting all together, as I will explain later, all the countries, all 13 countries of the river basin, and a case study in Myanmar, which in Myanmar, for many reasons, mainly political, it didn't go as planned in the project. So the reason why I'm most proud of you seen in the video is that for 4 years, we didn't have a publication. I didn't have a public. We had a couple of conferences here and there, but we're more focused on training people. So we're developing this kind of web-based applications. We're traveling to the African partners. We're delivering the training to engineers there, how to use our models and how to apply them in their own system. And with the KPIs, of the project, we kind of estimate that we train more than 500 engineers in those countries. Now some papers are coming, and some good papers, some Nature papers now, but it was not the focus of that project. So when we finished the project, if you looked at the publications, you consider that was a failure, and we spent a lot of money on doing nothing. But actually, we had a quite big impact in those countries. So as I said earlier, basically within the project we had water, power, and environmental engineers as well. So as I said earlier, the water engineers were just operating the river basin models that they had in their own manner, and they were doing a simple transportation model to see how much hydropower can be generated. And from our side as well, we started by utilizing all the water that we had on the rivers in these countries to actually generate hydropower. But the two are actually connected. And we try to basically see how we can bring together the water and the energy modeling into a single platform. So what we started doing in this project, we had our energy model, we had our water model, which are openly and publicly available on GitHub, PyNWR. And we also developed a communication engine. It was PinSim, which was basically responsible for linking the two engines together. And then we had different water inputs, water energy, weather data, modeling settings, and we also had the generation cooling, which was requiring some water from the river basin to operate. So we brought all this together under an AI basically model for multi-criterion design framework, looking at welfare, water, energy, food, environment, resource systems, in order to see how the different trade-offs work between the critical infrastructures. So this is how it works. So first we're doing the water power network simulation. So we're having the systems modeled together. So we started with a bit soft coupling. So the water team was modeling the water system, we're modeling our energy system, and then we had this kind of soft coupling and soft communication between the two models. Then we had one platform, one model for running both together with the spatial and temporal resolution that we're defining. And then as a first approach, we used meta heuristics to kind of select the variables, and then basically this was continued until we reached basically the water energy portfolios evaluation. We're achieving spatial and sectoral benefits for both systems. Okay, this is just a simple system which I will skip to go to the, for the sake of time, to go basically to the nice example that we did for Ghana. So for Ghana, we had the water and the power utilities as partners within the project. So they gave us basically some tasks in order to achieve large-scale development and penetration of renewables in the system, supported by the Akosopon Dam, which is in the south of the country, which is the largest installed generation plant with a capacity of about 1 gigawatt. So the electricity portfolio, the generation portfolio, of the country was something like this. So there was about 50% of hydro, 30% of gas, 23% of oil. And then we try to see how we can penetrate more and more renewables into the system. So this is the equivalent network we built for Ghana, which is currently being utilized by the utilities there. Where you can see there are wind farms, solar, dams, electricity, water system, and so on, everything into one model. So looking into the design challenges that we had, so basically we needed to meet the future energy demands of the country as it was evolving, reduce the emissions, minimize the hydroecological disruption, and no new dams. Which what meant is that we needed basically to rethink the way that they were operating their hydropower in the country. Okay, and the no new dams constraint actually was, because if you look, as Khadija does, in optimization, the portfolio might say, okay, build a new dam. But a new dam, as we realized very soon in the project, is not a simple case. The new hydropower station, because it had a lot of environmental impacts. So we had different objectives to minimize. So you can see that basically those objectives were spanning across different sectors. So we're minimizing the low curtailment, the hydrological alteration, the crop yields, the floods as well that we're having in the system, in the country. So it was spanning basically across the whole water, energy, food, and environment spectrum. The decision variables we had was adding more renewables, solar, wind, and also biogas as dispatchable renewable generation that they had plenty of resources in the country, building new transmission system, and as I said, rethink a bit the reservoir operation. And then we had different scenarios, intervention scenarios as we call them, just updating the operating rules of hydropower, updating the rules plus transmission line expansion, and then plus adding some bioenergy in the country. So as you've seen in the video, what we did, instead of going, let's say, yes?
Can you go back to the previous slide?
Yeah.
How do you model these, the objective function, these hydroecological alteration? How do you put that in the model?
The hydrological alteration.
Yeah.
Of what I understood, that was coming from the water colleagues. That basically has to do with the amount of water you are using from the reservoir and how that basically affects the water flow on the river. Yeah. Okay. I don't know if I covered you.
I just wonder how you put that
Yeah.
in the equation.
That I do not know. That is something that I was doing the energy part, and they were doing the water part.
It's not a matter of equation, because we have this kind of stuff between Turkey, for example, and Mesopotamia, where you build a big dam, you know this, and we have problems with the row of the water in Mesopotamia, so that it's not even between the states. Here is one state. Between the states, how much flow they want Mesopotamia, the Iraqis, for example, with the Turkish government. This is a kind of another thing, it's a political issue. So the flow, usually it's controlled by the requests of each country or of the citizens. It's not a mathematical thing.
Yeah, and I will talk about that the trading issue. I will address it later, yes. So what we did in the first meeting we had with the Ghanaian authorities, as academics, we went there and we said this is the optimal solution for the country. And then because there were different kind of engineers, authorities in the room, they told us, okay, what if you consider the crop yield? What if you consider, as Juan said, the impact of hydro ecological alteration and so on? So it was difficult to basically using these objectives and these decision variables to actually come up with one portfolio. So what we did, we defined hundreds of portfolios, which each line of this actually presents an investment portfolio for Ghana. So we kind of use this kind of parallel plot diagram for the utilities of the country. And for each of the scenario, we're having this metric and we're showing basically how it behaves and how it affects the different sector in the country. So once you do that, as we've seen in the video earlier, and you start putting filters into how much, for example, transmission line expansion you want, or you can afford, or you can build because of environmental reasons, then you can start seeing how the different metrics behave. So if, let's say, we put a filter there that we don't want any transmission line expansion, then we can see that basically the hydro was just supporting the base load. The renewables penetration was kind of reduced, because the higher we go in this metric, in this diagram, as we said, is the preference. So the higher we are is the best, is better. And we're also not doing very well in terms of load curtailment and also emissions in the country. If you do hydro peaking, so hydro peaking is basically not just operating your hydro generation for base load, but you actually do the balancing for renewables. We can see that basically the renewables are increasing a lot, but when you do the hydro peaking, you have a big impact on your hydro, on your water metrics. So you actually have a lot of impact on your water consumption, but because of the penetration of new renewables, the emissions are improved, and also the low curtailment are improved as well. Then you start playing with different filters here. So for example, if you build new transmission network, then you reduce the environmental impact here, and then you also kind of optimize in a way the metrics for the other sectors as well. So what we called to provide, let's say, a solution for the country, because we were asked to provide a solution, we came up with what we called a compromise solution, not an optimal solution, but a compromise, which was basically achieving a kind of compromise between the different sectors that we had in the country. So this basically, what we see here is the portfolio for the compromise solution that we had for the country, which was basically building some new transmission corridors between the different regions of the country. And then we have how different technologies, energy technologies, will penetrate in the country, from solar PV, some storage, wind, biogas, and also transmission system. So this compromise solution achieves low cross-regions transmission expansion, higher expansion in the southern part of the country. And the reason why it's in the southern part is because the big hydropower stations are actually in the south of the country to achieve the hydro peaking and then balancing, and also higher biogas penetration in the north where the resources were more available. And these diagrams just show a bit with box plots how the different technologies penetrate in the different region. And actually these kind of results informed the strategic energy plan of Ghana, looking 10 and 20 years ahead for their strategic energy design. Okay, these are just some other results. So the other case study we had was for the Nile Basin, as we said earlier. So we built, as you can see here, we built basically the integrated water energy network of the whole Nile Basin. So this is available. We have this model, and this work was published recently in Nature Water. I think it was last month that was available. So it's a very nice piece of work, and I think the model is already available in GitHub to be used. So we simulated all the energy and water system from Tanzania all the way up to Egypt. So it has all the technologies, both from the water and the energy side, into one common simulation model. So as the colleague just said, how the trading works in this kind of complex systems, because it's pretty much a political topic. So what we addressed in this paper, there was this new dam that was built in Ethiopia, the Gerd Dam, the Grand Ethiopian Renaissance Dam. Yes, thank you again. So basically, there was what they called the Washington Draft Proposal that was allowing trading only between Ethiopia and Sudan from that new dam, and no trading between Ethiopia and Egypt. The concern was basically when we went into forums with all the system operators and ministries about this matter, their concern, of course, was if you use a lot of water upstream in Ethiopia, how it affects the water flow downstream in Egypt. And there was a kind of a lot of heat in those meetings. So we tried to see if energy trading can actually help solve this kind of river basin conflicts in order to basically share the benefits of that big dam across the countries on the Nile Basin. So we defined different scenarios here. We had the low trade, the medium to low, medium high, and high trade, and we basically increasing by 100 megawatts each basically trading scenario compared to the Washington Draft Proposal. The Washington Draft Proposal was something coming from the United States to basically explain, to propose how the Gerd water releases should be used. So we took that Washington Draft Proposal and we increased it gradually by 100 megawatts, as you can see here, starting with 100 megawatt, 200, 300, and so on, and to see how this affects basically the energy trading and the water resources in the region. So these diagrams, which I will not go into much detail, so they are showing basically over the period of time how the Gerd water volume changes for different kind of water uses and trading, energy trading scenarios, and how the Sudan, Egypt water supply deficit changes under this kind of different scenarios. So these results, accompanied with some more results that we have in the paper, you can go and read the paper if you want more details, how everything was modeled, simulated, and compared. We try to basically see under different trading scenarios how the energy and the water resources and deficits change for the countries. So we try to basically give a kind of proof of concept, if you like, if you use in different ways the new dam that was built in Ethiopia, how that affects the performance and the resilient performance, if you like, of both water and electricity systems for these big countries of the region. What we also did, because coupling the water and energy systems is quite complex and it depends on many assumptions, we try to see basically how those modeling assumptions can affect the performance of the model. So we consider different sensitivities to water availability, race integration, power network stress, temperatures, as well as including or not including different factors in our model. And different factors, we mean if we have a unique commitment for the power system, if we have the losses, if we have the hydraulic routing as well of the water system, which affects a lot the performance of the power system itself, and so on. And then we came up with different metrics when it comes to the cost of electricity and water consumption, as well as reliability metrics when it comes to the load shedding computational cost under the different assumptions that we had. So we tested basically thoroughly our models under different modeling assumptions for both systems. What we also did, we took different climate scenarios that were provided from some partners in the project, and we tried to see how those climate scenarios can affect different technologies that we're having in the region. So these basically nice colorful pictures show just some examples of those analyses that we did on the average PV generation, wind generation, thermal, as well as a daily rating of the overhead system that we're having in the countries. And the overhead system is something very important because I'm sure some of the colleagues here might be from those regions, but the temperatures can get very high. When I visited the Emirates, it was in August, which was a very poor decision to visit Dubai and Abu Dhabi in August. You could see the transmission lines actually sucked very much. So it was getting into the distribution level, the distribution level height. So those constraints, we quantify the impact of climate change and different temperatures, water availability, and so on the resilient performance of PV, wind, thermal, and overhead line ratings. And what some other colleagues did in the project, which I was not involved directly in this work, is to try to develop what we call the economic policy for sustainable development. So what they did, they basically identified the sustainable development goals for the different countries, and then they try to see how different policies that they have in place can interact within this kind of multi-sector and multi-actor environment that we have in this kind of river basin infrastructures in Africa. So this is a very nice article. This is in Nature Communications. If you're more interested more into the policy aspect of this work. And of course, if you want to learn more, you can visit the website where you can see different articles, position papers, as well as different training platforms that we used for the African partners. How am I doing with time, Pierre? Very good. Okay, so.
Can I ask a quick question about the DERT study that you did?
Yes.
So what was actually the effect of the increased trades on the water volumes that could be released? Because at least from what I understand, the concern is that not enough water will be released downstream, and that somewhat the increase in trades facilitated that also more water was actually released.
Yeah. So what we noticed that the water deficit, of course, was increasing, not dramatically, but it was increasing, which Egypt was not very happy about. But if you consider the energy trading, of course, that my argument to that is that there is no market yet in the region. I think, if I'm not mistaken, there is a market in the Southern Africa part, a power pool, as they call it, but not in East Africa power pool. So in order to do this kind of energy trading, you need a market. You need to give a price to what you are trading. So if you look in all the metrics together, Egypt was gaining from the electricity trading from Ethiopia, Sudan, but it was losing from water. If you try to counterbalance from a mathematical academic perspective, it was balancing off. But if you look at it from, if you like, a political or a social perspective, a water deficit in Egypt because of increased water consumption in Ethiopia was not very much desirable.
But I'm not sure how far you know it, but obviously if, let's say, Egypt is importing power, then they will also rely less on the hydroelectric power plants they might have, which again actually
Yes.
is more beneficial for them.
Yeah. Yeah. I will tell you later about an incident that happened that it might not be very wise to say openly. Okay, so very briefly, some relevant work about this kind of hydropower optimization is a work we did for the Crossbow project, which is a Horizon 2020 project. So within this project, we're tasked to basically build this kind of regional storage coordination center. For this part, we looked into the Serbia-Bulgaria interconnected network, into the Balkan area in southeastern Europe. So we try to build this kind of regional storage coordination center, which would sit in the coordination center in Belgrade, to try basically to provide kind of, as we say here, increasing penetration of renewables, solve this kind of congestion management, and also provide frequency stability for the countries. So as I mentioned, the idea is to actually have this kind of storage coordination center in Serbia, which will try to co-optimize the renewable penetration in the region of Balkans in Southeast Europe, in the southeastern countries, in the southeastern European countries. So the idea is, if you have dispersed, let's say, storage in all the countries, how this storage can be coordinated using the tie line power flows in order to improve basically the renewable penetration in the region. So this is how it looked like. The idea is to basically have the measurements coming from the energy storage units, the hydro pumps, into the optimizer, which was basically optimizing and utilizing as well wide area measurements in order to come up with a security analysis and to return basically the green status to the optimizer to send back the set points to the storage units and the hydro pumps that we had in the region. So we considered the interconnected Serbia and Bulgaria system, and we used different storage scenarios, so no storage, national storage only in Serbia, as well as regional storage in the interconnected Serbia and Bulgarian network. And we assumed some wind basically in the northern part in Serbia. So these are basically some results which look pretty obvious. When you have no storage, we had, of course, a lot of risk curtailment because the system could not handle it. Then when you consider national storage, which is the black line here, the curtailment of renewables is reduced a lot. And when we are looking at regional storage, so co-optimizing the storage we had in both countries in a coordinated fashion, we see that basically the risk curtailment, which refers mainly to wind, was reducing quite a lot for both regions. And then we looked also how this kind of cross-border storage can provide frequency regulation for the countries. And then we've seen basically with this kind of fast hydropower services, the frequency under different disturbances can be improved significantly. So what we did at the end of the project, because we had to actually show and demo, we were receiving real-time data, sort of close to real-time data, in our Manchester platform, our Manchester server. And then we're returning basically set points to a big hydro pump station in Serbia. We were hoping that basically they were kind of going to take actions based on those set points. But they were just confirming that they were receiving the set points in their control center and that they were not doing anything. And because, of course, they couldn't interrupt the operation of the largest hydropower station in Serbia. And by using this kind of set points, we were sending the set points and then they were simulating using their simulators, the water release and the hydro generation, and they were basically kind of optimizing their reservoir performance based on the set point we're sending from Manchester. So this basically helped a lot improve the frequency and the voltage operation of the system. So then talking very briefly about this kind of resilience now of water and power systems. I was involved in the IEEE task force of water and power systems, and if you want to see more about this task force, we published the technical report towards the end of last year. So I was responsible for the topic of resilience of water power systems, and we tried to basically come up with different conceptual frameworks on how the two systems might interact with each other and might affect each other under different disturbances. So from the power system perspective, we had the infrastructure damage as scenarios and the resource limitation as well from the water system. And then we're trying to basically see what potential impact they can have on the other systems. So from the power system, a cascading impact to the water system could be a disruption of the pump operation or limited water treatment. And also from the water disturbance side to the power side, of course, reduced hydropower generation and some limitations in the thermal unit cooling. So what we also did with some colleagues from the University of Utah within this task force, we tried to see how we can actually do a kind of coordinated recovery of the interdependent water and power distribution systems. So we built a couple of models of power and water looking at the distribution level now. So we had basically the power distribution system where we simulated different disturbances and different parts of the system. And then we try to see how we can minimize the outage propagation in the water distribution system. And then, on the other hand, we try to see how we can treat the water demand as flexible and controllable demand to support the electricity distribution system. So this is how it worked basically. So we had the power distribution system with power demand, storage, line repairs, line outages, the water distribution system. And we had basically this kind of framework, as I said, about the coordinated recovery following and disturbance. And we had this kind of loop between the two systems where we had the pumping and the power generation kind of treated as flexible demands in the two coupled systems. So this is a test system we used. We used the IEEE 33 bus distribution test system and the 16-node water test system, where we had water reservoirs, tanks, pumps, a small kind of hydropower pumps within the water distribution system. And then we simulated basically different damaged lines in the water system, in the electricity system, and how that can affect the water distribution system. In the right-hand side, you can see different approaches that we applied. So we had basically the uncoordinated approach, and the coordinated without batteries, and the coordinated approach with considering batteries, energy storage systems within the electricity system. And we see here basically the ratio of served power and the ratio of served water in the two systems, applying the coordinated and the uncoordinated approaches. So within the paper that will be hopefully published soon, you can see how the metrics behave for both systems. Yes?
When you say water power, you are limiting the thing on the hydropower or the heat pumps?
Sorry, what?
We have the ocean power. We have the waves power.
Yes.
It is water.
Yes.
So we don't put this in this terminology. You use only water power from the hydropower.
Yes.
Also, you don't use from the nuclear.
Nuclear, no. No.
You use water.
Yes, you use, yes, no, but we didn't touch upon that, no.
So it's only for hydro?
Yes. So basically we treated the water assets as flexible demand for the electricity system. So the water pumps and all the assets that require electricity, we find now we're trying to improve this work with some water engineers from the Technical University of Israel. We're looking basically to understand the minimum water level that they would require to continue functioning properly. So we receive that input from the water engineer side, and then we try to basically constrain in a way the electricity that we're providing to the water system, but also at the same time maintaining their reliable functioning, because we cannot cut water to cities.
We have a lot of water, but it's another thing.
Sorry?
We have a lot of water. You mean sweet water, or we have very sweet?
It depends where you are. In Cyprus, we don't have much water. Yeah.
I mean, if we have the energy, we can take the water from the sea.
Yes. Yes, you can do that. Yeah. We have desalination station in
We are
Cyprus.
doing this already in Saudi Arabia and in Cyprus.
Yeah. Yeah. That requires a lot of energy as well, though.
It's another thing.
That's yeah.
This is a matter of research.
Yes. Yeah. Okay. So what we're doing now, as I mentioned, with the colleagues from the water engineering school from Israel, we're trying to basically develop different communication approaches for the water and power systems. So we have the power distribution system, we have the water distribution system. We have different events, so we activate basically the emergency control for the two systems. And then what we do first the inner optimization from the power side. So we put, okay, these pumps penalties was put from the water colleague, which is kind of, it's constraints basically to the water distribution system. So we put the constraints, then they kind of minimize their pump power as much as they can. So they return basically the emergency pump schedule back to the electricity system in order to come up with, let's say, an optimization and as much as possible reduction of the load shedding in the electricity system. So again, we're facing basically the water distribution system as a big flexible demand for the electricity infrastructure. So this is the test system we used, again, for the 33 bus system. Now the water system is simpler and a bit different. And we assume that because of a disturbance, we go completely off-grid. That was a big assumption that the water colleagues did, to basically operate this as a completely independent water energy distribution microgrid, basically. So the important findings, though, here is when we run basically in different scenarios, different contingencies, and different scenarios in the systems. Here we have the load shedding for the independent decision making. And here we have the load shedding reduction as a function, basically as a benchmark, when we have this kind of independent operation of the two systems. So we can see that if we are in this kind of scale of load shedding, so we are talking about not major disturbances in the electricity system, so you have basically the paths to actually utilize the flexibility from the water system. The load shedding reduction in this part is quite satisfactory. So we achieved basically for most of the scenarios above 5 or 10% of reduction of the load shedding in the electricity system. As we move on to bigger, let's say, disturbances, and bigger disturbances, we mean more and more contingencies in the electricity system, you don't basically have the infrastructure to utilize the flexibility services from the water distribution side. So whatever approach you define, being comparative or communicative or whatever it is, the reduction that we're seeing for very big disturbances was reducing quite a lot. So you will need, in one way or another, to have the infrastructure to actually utilize the flexibility and benefits from both sectors. So concluding, Okay, so just to conclude, looking at our national energy and climate plan in Cyprus. So I just wanted to highlight basically that the European Commission is calling for this kind of multi-energy and multi-sector coordination, moving ahead to achieving our carbon targets. So they are talking about energy, electricity, heating, cooling, transportation, and so on, in order to reduce the carbon emissions in the country. And Cyprus, keep in mind that for the time being is isolated, so reaching those targets is very challenging. Now we're being interconnected with Greece, with Crete, and the plan was to interconnect with Israel as well, but that plan, for obvious reasons, is put a bit on hold now. But we're hoping to make things easier when we're interconnected with Cyprus. But reaching those targets is quite challenging for Cyprus. Of course, the key messages that we have from the report that we submit to the European Commission, which had a lot of comments, is of course increasing the penetration of renewables, energy efficiency and reduction of emissions, and also looking at this kind of human-oriented and community-centric approaches as we move on. Is the usual, the known concept of energy communities, basically. So there are many challenges that we have in the island. If we understand basically the risks of increasing penetration of renewables, if there is adequate coordination between the different sectors, between the different ministries, and so on. And we define basically as an academic community different requirements moving forward for Cyprus, including new tools, more cross-sectoral approaches for Cyprus, because at the time being we're doing everything quite interdependent, and also understand better what different scenarios mean from the perspective of socio-economic benefits for the island. So that was it from me. Thank you very much. I hope it wasn't very long or tiring, and I will be open to discussion and to questions if you have any.
Thank you very much.